start that. So I'd like to introduce our speaker today, Associate Professor Mike Meylan from University of Newcastle. Mike obtained his PhD from Otago University in New Zealand, and following that held positions at Massey University and the University of Auckland before moving to the University of Newcastle. Mike is an expert on elasticity and fluids, hydroelasticity, and that is, I think, what he's going to be talking to us about today. So I think I'll hand right over and let you take it away, Mike.
Okay, thanks, David. And thanks a lot for inviting me to give the colloquium. It's a bit of a shame, actually. I did have plans of driving down when I heard the invitation to Macquarie. So I think I was still sort of getting used to this COVID world. And I'm also kind of aware that our attention in Zoom is not all that great. So I'll try not to go for the full 45 minutes, and I'll try to, the talk is not too dense, okay? Because I'm sort of aware from attending my own Zoom meetings that I'm usually doing 5 or 6 other things at the same time, checking emails, etc. All right. So the topic is hydroelasticity, which is basically a problem where you've got elastic bodies coupling with fluids. So it combines, so fluid mechanics and elasticity are generally held as separate domains of knowledge, so it requires a knowledge of both of those. And it's one of those cases where you need to have a situation where the fluid forces are sufficiently strong that it's going to bend the body, or the elastic motion is sufficiently strong that it's going to move the fluid. So for lots of examples like aeroelasticity, for example, I had a great ride on an A380 and it had some turbulence and the whole thing started to bend up and down. And I was at the back of the plane moving at about 4 seconds period. I think the amplitude must have been close to a meter or something. This thing was really bending. But that would, that forcing the plane moving in the air doesn't really affect much. So it's not, the air is just not dense enough. So you can treat the fluid, the air separately. And as always, fluid mechanics is a lot harder than elasticity. So it's usually the fluid that's the problem. And we get lots of people, especially with some of these trendy areas like wave power, you get a few people sort of leaping in, and they've been, especially people who are successful at getting funding, jumping into that bandwagon, not knowing any fluid mechanics and not getting terribly far. So it's the fluid is always much more complicated than elastic body. Elastic bodies don't do terribly much exciting unless they start breaking up. Whereas fluids can do all kinds of crazy things. All right, so we'll just I'm going to talk about 4 different problems from hydroelasticity that I've studied. So there's a few colorful pictures here. Some of them are quite beautiful from a very special place, which is this Antarctica. So you get an idea here of this sea surface covered in these broken pieces of ice. So there's lots of interesting problems around the interaction between waves and this ice. And this is the problem that I started on my PhD and that I've studied a lot. So basically, you can sort of imagine this picture up here that waves have broken up this ice. That seems perfectly reasonable. But it's hard to understand why elasticity comes into it. But the thing about it is that this piece of ice is, the scale here is much bigger. That's not a ship there, that's a giant piece of rock. It's an island. That's some Erebus or something there in the background. One of the, it's a very, very deceptive place, Antarctica, because that's like thousands of meters high. You get very clear air, but this is huge. So, and it's not very thick. So it's like half a meter thick and it's hundreds of meters across. And something that's half a meter thick and hundreds of meters across is going to flex and bend. I mean, how bendy something is really about how long it is compared with how thin it is. So these are this is bendy. The waves are coming in here and they're bending this ice, and you get at some point, some distance from the ice, there's no stress at the edge. That's one of the boundary conditions. At some point, there's a peak in stress at about here, and it's breaking the ice off into these regular sized pieces. So this top photo is kind of beautiful, but it's not normally happens. Normally the waves are much more complicated and a bit messier, and they break it up like this. And these waves here, the size of the pieces is to do with the size of the wave. So these break pieces of ice and the thickness of the ice. And there's a picture of the ice. And lots of people are interested in why ice breaks up, how much it forms. It has heaps of super important roles in the climate system. Do waves play a role? And then there's also safe shipping in this sort of environment. And the shipping problems become much more interesting and topical because the United States would like to make the world safer for democracy. And one of the places, maybe this is prior to Trump, I'm not sure what he wants to do, but they wanted, the US military certainly wanted to be able to control the shipping in and out of the Arctic if it became a place of shipping. So they want to understand, when is it going to be safe to send their battle fleet into this ice? Because if you've got big wave events, you don't really want these big pieces of ice getting tossed around and hitting the side of the ship. But what happens is that actually the waves, once they hit this ice, they just kind of stop propagating. It really dampens them enormously, and especially the short waves. Okay, and there's a great picture here showing you that the waves, there's ice cover breaking in the process of breaking up. So lots of these photos are not necessarily the most typical situation, but they're sort of the most colorful, and it illustrates the point here. You can see that they're not breaking up quite as regularly as you might imagine here. It's that other picture. This is a bit more realistic, and then they'll continue to break up and fracture. And once they're fractured, the ice loses a lot of it starts to melt and can get very rapidly moved around by wind and waves and currents. Whereas when it's solid like this, it's quite robust. So, and it has a big effect as this big formation of this massive amount of ice around the Antarctic has lots of interesting effects. And you can imagine it reflects all the energy that's coming in from the sunlight. So the ocean starts to warm up once it gets in here, all the energy from the sun. Because even in the Antarctic, the sun's quite strong in summer. Surprisingly strong. It's not, you know, it's not like in winter, it's not so great because there's no sun. So I'm hoping this is going to work, this movie, and you can watch it. This is was put together by Ken Golden. I quite like it, but it shows these waves moving through the marginal ice zone. So we're interested in trying to understand this process. And so this is the ocean. This is a great picture here. The waves, you've never seen the ocean surface moving like that, sort of undulating, because all the low frequencies have been removed, have been filtered out. Okay, so what we're trying to model this process, there's two ways you could take this process, and both of these have validity. One is you could think of this as a continuum and try and understand it and model it as a continuum. And one is you could try and model it as a individual flow scattering, individual piece of ice interacting with a wave and scattering, and use multiple scattering. And we've largely developed theories based on that multiple scattering, solving for these individual flows. And there are other people who've worked a lot on these more continuum-based models, and they merge one to the other because the ice, as the waves break it up, the flows get smaller and it becomes more like a continuum. It's actually not properly understood how this acts as a filter, and that when the waves propagate through this ice, the energy disappears, and there's some process that removes the energy, and that can't be scattering, because scattering just redirects it. And we don't know what that process is. The physics of this is fundamentally unknown, which is rather bizarre, because it's very hard to work as a mathematician if you don't know the physics, because you don't know where to start writing the equations down. All right, so let me just jump forward here. Yeah, this is the movie here showing the process of breakup. It's kind of hard to interpret. This is up in the Arctic. This is Alaska here, and these are wave buoys drifting around, showing the ice. It's the I'll see if I can explain to you what it means, but basically it just shows you what happens here, where you get this huge wave event which will come tearing through here and start to break this ice up. So this blue here is showing the wave height. And these are wave buoys drifting around. It's supposed to show the amount of waves they're seeing here. Okay, so this is from some measurements of the process. There's been lots of measurements of this wave process. I'm not really an experimentalist, and I don't really enjoy analyzing data, because I think that's, you know, for someone else to do. There you can see the waves coming in and pushing the ice around, and you can starting to get big wave events coming into the Arctic here and melting up the ice. Okay. I'm never sure how exciting this movie is when I see it. It was very amazing for the guy to make it and to overlay it. It was quite a lot of work from the person here. All right. So you get an idea here, though. It's very hard to factor out from these measurements. They're just a sort of giant mess because the buoys are moving around all the time. You don't know where the waves are coming from, and trying to work out from measurements how far the waves are traveling and how they're being attenuated is really tricky. So if I can just get this to jump forward. All right. So I'm jumping here to another problem in hydroelasticity, and then we'll come back to them because it's very closely related. And this is this very large floating structures. So these have been proposals, and they have to build floating runways. There was a proposal in Japan, and we'll talk a little bit about why you never build a floating runway, because I think that's one of the first things you can quickly work out, why we don't build floating structures, because we've got everywhere in the world, you know, the great colonizing powers went around and established these port cities in, you know, Mumbai and Shanghai, Singapore, and so you know there was a natural thing to build cities, and they've become these big mega cities. So there's stacks and stacks of cities that are built close to water. So you think, okay, we could try and reclaim some of that land, and because we can reclaim by filling it in, but we could also build something solid that would float. And it's lots of advantages to building something that float. You can build it in deep water. It's going to cost you stacks less to build and all this stuff. So the Japanese had a plan, and they built this floating runway. But they called it mega float, but there's a big problem, and the big problem is waves, because essentially the waves come in here and they're going to either overtop the thing or start to make it bend. But it turned, and there's a lot of research around the construction of this floating runway in Japan, and it's almost identical to the research that was done on floating sea ice, because the equations of motion are the same. There's actually just change a constant of motion. And here's another proposed figure here. And there's a, so I talked a little bit about these very large floating structures. There's an airplane landing, and they actually land planes on the ice in Antarctica regularly. There's a runway, much bigger planes than this. This is the Hercules, but they land the I can't remember what they're called, the Galaxies or something. There's massive, the one that the 747 lost to, because it was originally designed as a military aircraft, but they didn't get the contract, so they turned it into the Boeing 747. But there's a landing huge 747 signs on aircraft on the runway here. So it's kind of similar to this. The only difference, and when this thing lands, it creates waves that run through this hydroelastic waves, which people have measured and which have really interesting properties. You get like a wake, I mentioned that wake traveling through from the plane landing. All right. So I'm just going to show now some experiments that we did in a wave tank to try and investigate this problem, and then we'll talk about some simulations that I did of these experiments. So this is done in the wave tank in Plymouth, and it was done by Alessandro Trifoli, who's currently at University of Melbourne. And here's the picture. This is the experiment, and you can immediately see that this is the flexible. It's a piece of plastic. It's supposed to be a floating runway, or a piece of sea ice, right? That's how they move, they flex. And this thing here is, you can see the flexion. You can also immediately see this massive problem, and that is that there's not much freeboard on these pieces of ice, or on these, and that your intuition tells you if the wave height is much higher than that freeboard, and the freeboard's not a lot. And even on a piece of ice, it has density close to water. It's 90% that of water ice. You know yourself from ice in the glass. So you're going to get a 1 meter piece thick of ice is going to have a 10 centimeter freeboard. So a wave, and you've been to the beach, there's waves a lot bigger than 10 centimeters, right? I've seen them down at Newcastle Beach. And hopefully, even though you guys live in Macquarie, you occasionally make it out to the beach, but you get big waves. They're going to just break over the top and cause all this stuff. And that's another whole phenomenon which we'll talk about. So the problem starts to get really interesting, just to try and model what are the physics of this problem. How would you model this thing you've just seen in the wave tank? Forget the anything else. Let's just try and model this. And so this is another shot from that was just a sort of test movie, a bit of fun. I think I probably made it on my iPhone, but this is an actual movie. And you see here, it's got these 16 markers that we're going to measure the displacement of these 16 points of this plate. And we've got a gauge here in the middle. So it's really interesting for me. I'm not super experienced with experiments, but you realize that in a numerical simulation, you get everything. You can measure is probably the wrong word, but you can simulate everything, the flow here, the height here, here. But once you do experiments, you only get the measurements at these 16 points. And looking back, and there's only one tide gauge. And of course, if we started attaching too many too many wave height gauges here, it would start to disrupt the motion of the plate. Okay, so we want to try and simulate this problem, including all the braking over the top. And this has been an ongoing project that probably ran over several years and quite a few publications to try and simulate just the simple experiment. So it was very fruitful collaboration, this. So what we do is we think, well, we take the elasticity and we work out the natural modes of vibration of that elastic body, and we can assume that it's thin, and we can exploit all this properties of thin plates. We don't need finite elements too much, or we can certainly simplify it a lot. We do need to use the finite element method, in fact, but it's because even for a square plate, for a circular plate, there's an analytic formula for the modes of vibration, but for a square plate, unfortunately, there's not. But they are orthonormal, and you can normalize them to have, to be orthonormal as well as being orthogonal, and they satisfy this equation here. So we compute those and we use those to expand the motion. This is a really good idea because it massively reduces the dimension of the set. So the problem of in something like a finite element simulation of a plate, you might have hundreds or thousands of elements, but you can project onto the spaces of modes and you can reduce the dimension down a lot. And this works, it scales right up even for doing huge containership models. So it's very advantageous. All right, so we then went through and trying to simulated the results and compared them and tried to look at what the effect of all that overwashing water was and all kinds of stuff here. I'll look through this figure, it's colorful, that's for sure. I'm not sure what it tells us, but it shows you the different modes here of vibration. All right, so this movie here is a picture of my numerical simulation versus the motion of those points measured by this Qualis system. And there's no cheating on this movie, I promise you, okay? Not a word of a lie. There's a lot of nonsense on the internet. And perhaps this movie is going to be part of the nonsense on the internet, this talk. But this is completely upfront. These are the measurements here. So this is the 1, 2, 3, 4 measurements. I've just simply taken the motion as a time history and then I've plotted it with a simulation. So the agreement's remarkable. Here's another picture here showing the motion. You can see it bending and, okay, obviously the scale's a bit exaggerated here, but this is kind of amazing because all that water flowing over the top's not in the simple model that I constructed here. So basically that fluid layer that appears on the surface is not strong enough to really force it. So this is, and what's interesting, when we tried to, even when we turned the waves at steepness up, this simple model, linear model worked really well. So we've got a really good handle on the motion of the plate here. We're pretty much sure our models are correct. Obviously, it's only validated in the lab, but I might just jump through this movie. I mean, the problem with these movies is that, I don't know how exciting it is, but this is like hours and hours of my life that I spent devoted to doing this. So I've got to get some value out of it because that didn't come cheap. This code, I had to code up a finite element. I was a bit stupid, and I did it back in the day when I was much younger. So I coded my own finite element and coded my own boundary element, coupled them together. This is a very complicated calculation. And in fact, to the best of my knowledge, it's not ever been done again. I did it in 2002, and lots of people have come afterwards and studied this problem, but they've always done something simpler. They've basically had more brains than I had and said, damn that, it's going to be a nightmare to code up. And you can't, unfortunately, you can't console your way through this to the best of my knowledge. I'm not an expert on console, but those solvers are not really suitable for this. You need a kind of boundary element potential flow solver, and then those usually work only for rigid bodies and blah, blah, blah. All right. So then we get onto this thing which Luke Bennett is my longtime collaborator from Adelaide. He coined it, gave it the name Overwatch, and it's become a really interesting thing to study in itself. And there's an untold lot of fun you could have modeling this. So this is the phenomena here of this water, these balls rushing up and down on the plate. And how do we model those? So we reckon the plate motion here, we've got a handle on. This doesn't really affect the plate motion too much. And that sort of makes sense because there's a whole huge amount of water here moving that's going to put a lot more pressure. But we want to understand how this happens. And for a floating airport, this would be a disaster, and that's probably why we're never going to build one, because it's going to be hard to land a plane. And for a piece of ice or something like that, once this water gets on there, it's going to destroy it. Now, the really weird thing is that nobody's ever seen a piece of ice with water rushing over the top of it. And you saw in those movies, you didn't see that. So we can speculate why that's the case. But it's pretty hard to imagine that that wouldn't happen and it certainly happens in these experiments. And we believe that it's something that, because what I believe is that as soon as this happens, the ice is just absolutely destroyed. And it would eat up that energy. And the very violent high wave events and not places people want to go and visit in their ships or anything like that. But the Aurora Australis, bless its heart, which has just been decommissioned tragically. It's a beautiful orange thing. It would not want to be in the captain would very quickly try and get it out of those very violent wave regions and near the ice edge, because it would be very dangerous for the ship. All right, what's happening here? Yeah, here's a picture of a simulation that was done of this Overwatch versus this experiment. So this is the, I'll just see if I can play that again. But you can see here how qualitatively it looks really like it. So we got a really good handle on it. And we used a kind of shallow water flow model to try and simulate that. And people have used more advanced methods using these numerical software, open foam, principally, to try and simulate this. But it's really hard to get this bending motion into those models. It's still not properly sort of done. There's a lot of work to be done on this. And then, these bores, they collide. And when you get colliding bores, you get jets, which are also phenomena that's really hard to model. I mean, fluids are just an amazing subject, infinitely fascinating subject. So much crazy happens. Here's another picture here. Okay, you can see these, the bores hitting, colliding, forming jets. And you can see it actually just lifting out of the water. We've really kind of ramped it up here. Okay. So I'm just trying to make sure that I'm on time here. I don't want to go and definitely don't want to go over time, because I think concentrations of everyone's, limited. So now we've got this is something I've become super interested in recently. And this is the problem of ice shelves and their vibration and what happens to them. And it's a really interesting problem. I'm not sure how important the waves are. There's lots of various evidence around the fact that the waves play some part in the breakup of these ice shelves, and it's just a really interesting. They're a really interesting object in and of themselves, because you've got this sort of glacier floating over the ice, and they float out for kilometers after kilometers. This is one here. It's 180 kilometers where you've got ice. This thing here, that's what you're looking at. It's a massive wall of ice, but it's not solid to the bottom. There's water underneath that. Obviously, this is floating a long way down, but there's water underneath it for 80 kilometers. And the whole thing does vibrate up and down. There's waves moving in it coupled with this fluid beneath. And this is a pretty fuzzy picture. I wish I've just snapped from the internet. But it shows the collapse of this Larsen A ice shelf. So what happened is, it's maybe very unclear, and I'm going to tell you what happened, so you just believe it. Whether this figure tells you that, I'm not sure. But it basically just disappeared overnight. It's January the 31st, March the 5th. Now, problem being that nobody was there to watch it happen. So we don't know exactly what happened. The satellite flies overhead and takes a photo, and then comes back a week later and it's gone, sort of thing. It's kind of surprising, but it basically happened much quicker than anyone imagined. It didn't just gently melt away, it just rapidly collapsed. And one of the theories that has been postulated is that it thinned, and as it thinned, it started to vibrate more, because the toughness of something is proportional to the cube of the thickness. Which is why you've got lots of I-beams around, right? And that's a great thing, and why thin things, you know, flex. You have to make something much thicker to stop it from flexing. So if it's thinned, so there's a certain critical thinness, and this is true, we haven't quite worked out what that is, where it'll start to vibrate more in response to wave forcing. And of course, just that, once you start vibrating this piece of ice, it's going to start to break up. It's riven with cracks and all kinds of weaknesses. It's not a solid, homogeneous sort of thing. These ice, this ice shelves are not like that. So we want to know, and there's some theory that there was a big storm that came in that sort of caused it, but you know, no one's sure. It's all speculation. So that does go right back to, there was one guy who was banging on about it forever. It's quite often the case with these sort of areas of research. So, and nobody was listening to him. So he had all these theories. He got a paper in Nature about it, and it was actually a theoretical paper in Nature. It must have been, it was a lot easier to publish in Nature back in the good old 80s, I think, from what I can see. But he thought that this was his theory, that it was, the breakup was due to vibrations. And there's a beautiful story about there's a nice tongue in Antarctica, and Scott, you know, the famous Scott of the Antarctic, was down there, and he saw the ice tongue and he saw it break. So we know for sure that it broke in whatever it is written down in Scott's journal. He wouldn't have made that up. And then they reckon from this guy here, Holdsworth, this guy that was banging on about vibrations back in the day, he thought it broke in the 40s. So people figured out, well, it must be about time it broke now. So they instrumented this ice tongue and had everything measuring the strain and all this stuff, and instrumented it for many years, and then finally gave up. It didn't break, took the instruments out, and everyone knows what happens next. It broke. So nobody was sure. Had it broken the week before, we would have known if it was suddenly it started to vibrate or whether it was some other process. But there was a very strong campaign of measurements of ice shelves and ice shelf vibration done by the out of the US, funded by the National Science Foundation. And what these guys did is they deployed seismometers all over the Ross Ice Shelf. So this is the Ross Ice Shelf. It's kind of hard to get a sense of scale here, but we're going from 70 to 140. Okay, so that's a long way. That's right across Australia. Okay, we're not near the pole here, but this is a massive area they covered. So these things are nowhere near each other. So it must have been quite fun to go and do this experiment, because you imagine the spot here. Now, I mean, this is before COVID, I've got to say this, but I mean, now maybe it's a bit different, but you know, everywhere you go in the world, if you go to Barcelona, it's crawling with tourists. Very hard to get away from people, but this is the spot here. You'd be very hard. This is not overcrowded. This spot for sure. It'd be quite difficult to get to. But there's a big, of course, there's actually, from a modeling perspective, this is a terrible idea what they've done, because this whole thing's way too complicated, way too difficult, and we can't understand it. And these are far too far apart, because we're going to get measurements here every millisecond of these seismometers. I'm exaggerating slightly, but we're going to get very detailed measurements in time, gigabytes of data. So we can do a Fourier transform in time here brilliantly, but we can't Fourier transform in space. Forget it. We've got far too few measurements. So from a modeling perspective, we'd like thousands of these things, or we'd like some simple structure. But anyway, that's what they went and did. And what did they find? Well, they found that it was humming and vibrating in response. And they got this picture here where you can see a swell wave arriving, traveling deep into it. Okay, and the reason it's the slope here is because those swells, the long waves arrive first. This is a typical pattern of swell, and this is an amplitude. And they got these infragravity waves that bounce off here. So they even found it responding to tsunami waves. And that's actually something I'm studying right at the moment, is what effect tsunami waves have on these ice shelves, trying to simulate it, but with a PhD student. So they got this thing, it's measuring and it's vibrating. This is what really got me interested in this problem myself, because I thought, okay, this for sure, it's real here, this thing's moving. And we don't want the Ross Ice Shelf to break up, because it would be a bit of a catastrophe. It wouldn't immediately raise sea levels, but once all that ice melted, because even if all that ice melted, it's not going to raise the level of sea because it's already floating, but it's holding back a whole lot of ice pouring out, and there's lots of reasons. It would be a bit of a freak out if it happened. And there is evidence that the Ross Ice Shelf did just spontaneously break up. So it would be, if it happens, it would be like a thing, you know, okay, wow, global warming's really kicking in here, guys. We've got to be, this is serious. But I'm not, I'm not telling you it's about to happen now. It's been there for many millions of years, or many hundreds of thousands of years, I should say. All right, but there you go, it's vibrating away. And then this is a simulation that we've just done of these waves and how it vibrates. Obviously, this amplitude is really exaggerated. This is just some preliminary results. So we've managed to simulate this, and we've got to build a model, a much more complicated model for the ice shelf here, using finite element right through the thing, coupled with some kind of fluid model here. So the scale here is exaggerated massively. Okay, just remember that this is kilometers and this is centimeters. So you're not going to see it bending like that, but that's the kind of pattern of the bending. And here's the thing with it thickening. You can see what happens here. It becomes much tougher here. You can see it bulging and moving back. It's a really interesting problem, and we've got a lot of maths here behind this. A lot of work's been gone into this, and we've got it. We sort of feel like we can conclude variable bed and all kinds of stuff. So we're a very long way down solving this problem. But there's a really interesting problem right here on the boundary. What the heck do you do when this flows into the ice shelf? There's not. So we've just applied a rigid boundary like it's glued on here, but actually we don't know what the boundary condition should be here, and that's got lots of interesting consequences. All right, so the final, this is the fourth, we've had 3 topics, okay? So this is the fourth, I promised you 4, and this is the bending of container ships, which is another interesting hydroelastic problem. It's a lot more complicated, the elasticity, because the elastic bending of a container ship is quite a tricky thing to work out. Now, this has really been the most well-funded area of research because now everything's changed because of COVID, but I suppose that's not entirely true, is it? Because we're still getting stuff shipped from China under COVID. Ships are still moving, so it's just humans that can't travel. But this, imagine, look at this ship. It's absolutely massive. Now, if you make a bigger ship, you made the ship twice as big, you're going to be able to carry 8 times as many containers, and it's not going to cost you 8 times as much to make it, and it's not going to cost 8 times as much to drive it around the ocean. So the bigger the ship, the better. Basically, it's more efficient, and they just keep making ships bigger and bigger. Now, there is a more problem that if you decided to make this thing twice as long and twice as wide, where the hell are you going to have a shipyard big enough to make it, or a dock big enough? But you know, as always with humans, you know, you make the ship, people will make the dockyard. If you make the dockyard, you'll make the port, because, and here's this, the craziest part about the whole shipping is that it costs a bit in fuel to drive the ship. It costs almost nothing in the wages of the people who work on the ship. They don't cost a cent, basically. It's quite incredible if you think about the cost. And then stop for a second here and go, what's in this container ship? What's in this container? Well, you might be imagining it's all your worldly possessions, and that's great, but then they're probably worth nothing. To be honest, if it fell overboard, no one would care. But if that container there was filled with iPhones, imagine how small a box is, and they're $1,000 each. So whoops, that's a lot of money. That one container of iPhones is a lot of money. It might pay for the ship. So you definitely don't want this thing going to the bottom of the ocean, and somebody has to ensure that and say, when you're shipping these iPhones around the world, you don't really think about it, but someone ensures that it doesn't fall off. So they don't want the container ship breaking up. And they know that it has happened. Here's half a container ship. So there has been a few tragic accidents. They don't get publicized too much because nobody wants to talk about it, where these container ships have broken up. So everyone's been a bit worried about them. And this is a picture of just I took from YouTube of a container ship in heavy seas. So when you're moving to from Australia to New Zealand and your stuff's on a container, you don't want to be on this container here right at the front. This is supposed to show you down the gangway, and it's the whole entire ship. This is 300 meters, just bending and flexing and moving constantly under motion. So this is this hydroelastic bending of the ship. And when that ship bends, that fluid's really dense. It's not like a aircraft. It's radiating energy, and it takes a lot of energy just to move the fluid around it. This movie carries on. All right, and I don't know how much I need to show. I'm just going to make sure I don't go over time. So we've got to notice a few slides to go. These are some experiments where people have tried to look at different aspects of this problem. And this is, when it's driven by a wave, the sailors call this springing, and it's that, and then when it gets hit by a force, it's called whipping. They have a different name for them, and they feel really different, but it's the same mass that governs it all, as we know. It's just one, is that, you know, different Fourier transform of the frequency response. And here's some measurements from a container ship. And you can see here the things are running in very heavy seas. It's moving up and down. So they instrumented this container ship, and you can see it oscillating here, and then it gets hit by some kind of green water or something, right? Some huge wave smashes onto the end. It's like a delta function forcing. And then it oscillates at the same frequency here, but it starts, you've got this exponential decay of the energy back to this base state. So it's this sort of phenomenon that's really interesting to understand and try and unravel. So I've done a lot of work on this shifting from frequency to time domain, this transient response and this decay. And it's got a lot of interesting maths behind it. And I'll just try and touch on that now. Okay, so I'm going to have to put my foot down here. These are the modes of vibration of the container ship. So when we solve, I haven't shown any equations of motion. I've avoided all those, but we're going to have to hit some here. So what we do is we expand, whoops. We expand the motion. We've got the whole thing's governed by Laplace's equation, basically, because the fluid's incompressible and not moving too violently. And then we expand the motion of it in terms of these free modes of vibration, and we plug that in. And essentially, it's quite a simple idea. We say, if I move this container ship up and down like this, hand of God sort of stuff, it's going to produce waves which will radiate energy. So I know I don't know how it's moving, but I know it's moving in these modes. And if I knew this unknown amplitude, then I could add those up and reconstruct the field. And then we plug back that, so we take that unknown amplitude, but if we did know them, we'd know the fluid. And if we did know how the fluid was moving, we'd know the force, and therefore we'd know how much they were moving. So we just glue those two together. So that's just showing you there, that's a mode of vibration of a container ship, and it's a mode of vibration there for that simple plate. Okay, and that gives rise to this system of equations here, basically. So you've got mass, this is Newton's law, force equals mass times acceleration, that's mass times acceleration. This is some restoring force from the fact that it's elastic, so once you bend it, it wants to stiffen out. And this is the force from the fluid. It comes from two parts. One is from the fluid moving, and one is from just the static pressure pushing down into the fluid. And this is much simpler, right? Because it just depends on the displacement. It doesn't have to know the fluid motion. So we have, this is the sort of system of equations. It's kind of specialized to this problem of, it works for, but you have a body that's both rigid like a ship, and this one's disappeared. So it's been very well developed because it's so important for sea keeping. But it's just force equals mass times acceleration with this fluid motion, but we don't know the fluid motion. But basically, we can solve this problem by Laplace transforming it. And you end up, I won't go through all the details of it, but you end up with this system of equations that you can solve, which are now static, don't have time dependent, except for through this S. Okay, I'm zipping through this thing here. So you recover the solution from in the Laplace transform space for the potential based on these unknown modes. Okay, on the modes of vibration that you don't know the amplitude of. And you glue the thing together and you end up with a system of equation that looks like the following. Okay, so it couples it all together from the Laplace transform. This equation, this approach using the Laplace transform is my own work. So I'm glossing through this quickly, but if it's something that had to be nailed on my gravestone, and this is starting to get, you know, very optimistic, it might be this equation here or something like it. It's kind of, you know, it's quite a significant, so, you know, so it's something I'm quite proud of, having written down that equation of motion. But it's basically just in this Fourier space, you end up with a way to describe the equation of motion for these ships, for any sort of elastic body, and you can calculate the time dependent via the strange integral here. So, and it's got the special identity, which is rather bizarre, and it was unknown. And even though there's been lots of people working on this field, that this identity wasn't known until I derived this via this equation here. All right. And then what you find out of this whole system is this very bizarre connection with complex analysis. So this starts to get really hairy, and I'm going through this quickly, but essentially when you end up with a system of equations, there's a determinant here. And this is the contour integral. So you can deform this contour integral and ask, when does this thing here start projecting onto poles? It's quite surprising the sudden appearance of complex analysis, and what are the zeros of this system here? And this is a picture here of a visualization of the structure of the solution in the complex plane. It produces this really beautiful picture, and it has this twin pattern of zeros. This is a way of visualizing these singularities. So you end up with this, when you look at these structures, you end up with poles that are close off the real axis. People have, on the complex axis that you can project onto. There has been lots of work on this by various people, but it's never formed a kind of coherent whole. It's very much, under discussion. And then we can approximate it using this formula here. So this is actually something that I've worked out, which is really useful because it allows us to not have to go, because to go into the complex plane, you have to analytically continue the solution. And there's no way in hell you can ask these people who doing these containership models who've developed this very complicated code to say, oh, then they can calculate the response for a frequency of 10 Hertz. If you say to them, look, I want the response for a frequency of 10 plus I Hertz, they start to go, what the hell planet are you on? They don't want to go into the complex plane. But because it's analytic, we can use analytic continuation to get ourselves into the complex plane. And this is this expression here. Okay, and then you get this approximation of the solution here according to these formulas. Not super important, it's just what you get, just residues calculus. It's just the residues basically. So this is the final slide I'm going to show you here. I've done lots of work on this idea of projecting into these complex modes and understanding it and all that stuff, and for simpler systems. But this is the most complicated one I've done. So they started out with this containership model with an incredible number of elements, really trying to capture the entire superstructure of the ship. So they've got all the elements, and this is an incredibly sophisticated job to model this accurately with the finite element. But in the end, what they produce is these modes of vibration. So you get sort of twisting modes, they call them hogging and modes and twisting modes. And what happens is one of these modes, I can't remember which one, is a kind of twisting mode. And what it does is this mode here, when it oscillates up and down, it's going to make the water flow like a wave maker, and waves are going to radiate away, and it's going to be very quickly damped. But this mode here, you can get a nasty thing that happens where the wave starts to circulate around the body trapped. And so the energy doesn't disappear, and you get a much stronger peak in the response. And that corresponds in our system that we had before. It corresponds to that, the peak that corresponds to a zero in the complex plane close to the real axis. So using all this analysis here, I constructed this approximate solution here, and you can see here how it accurately calculates so mode, strangely enough, when mode 3 becomes really excited, because this is the dominant mode that it's excited, that mode 3, okay, the one that causes the circular wave. When that mode becomes excited, it actually drives the other modes into vibration, which is kind of weird. It's not what you'd expect, because these modes aren't orthogonal in the water anymore. So you get this, and so the approximate theory, not only does it tell you that this mode will be excited and capture it very accurately, but it also tells you how all the other modes, it gives you the actual real shape of the solution at that frequency. I was very proud of this. It's interesting that in practice, this very sharp vibration at this frequency is not observed, and people aren't sure why, but it's probably such a sharp peak that it's quite hard for energy to get in and out. Not only does it lose energy slowly, but it's hard for energy to get in. And also, if you started to, there's going to be some friction, perhaps from the container ships and the containers themselves rubbing, that causes it to disappear. All right, I finished there. I've gone the full 45 minutes, I know. So, but hopefully you've got lots of good email reading done, as well as paying some attention to the talk. So I've gone just finish here, and just hopefully you've sort of given you a pretty rapid tour of the areas of hydroelasticity that I've worked on. Thanks very much.
Thanks very much. That was a very interesting talk. Now I will let everyone unmute themselves. So if anyone would like to ask a question, feel free to unmute yourself and ask away, or type something into the chat as well.
Can I see the chat?
Yeah, if you go down the bottom, you should be able to see the chat.
Yeah, I'm not sure I can see a chat.
Can I ask a question?
Yeah.
Sure.
Hello, Mike. So as I understand, you compute eigenfrequencies on normal modes by finding zeros of determinant. How do you find eigenfrequencies? Computing zeros of determinant under the integral.
No, I found the determinant not very robust. So you've got the system of equations that you're trying to find a complex number, and this thing here you've calculated and that you're searching in the complex plane, and essentially you need this matrix here to have an eigenvalue that's 0. I just look for the eigenvalues of that. So the determinant of that matrix would be 0, yes, right?
Yes, yes.
But
yes.
I would search, the search technique I use is to search for when the eigenvalue is 0. And then I use a method, I've got a method worked out to, when I'm near the root, I take this matrix and its derivative and I look to search for where that 0 pair would be. So I'm looking for an eigenvalue of 0 for this matrix rather than the determinant. I look at the eigenvalues.
But your eigenvalues are not zeros. They are actually eigenfrequencies.
Normally you've got, so how to you've got this complex thing here. So this whole thing here becomes singular, right? At some point,
Yes.
this amounts to 0. Yeah, some frequency. So in a very simple system, you'd have the identity minus omega times some matrix, and then it would just be the eigenvalues of that matrix. But
yes, that's right.
yeah, but this is very complicated matrix. You know, it's very complicated function of the parameter S. It's an analytic matrix. It has zeros, but it's a very complicated function of that parameter. So it's quite hard to. But you're looking for when an eigenvector of a matrix is when the matrix M plus omega lambda, lambda times the identity, when that becomes singular. So you've sort of got how do I put it?
Yes, determinant is 0, and you find the roots of determinant function. Or not, maybe.
No, I can't. You can't. The determinant of this is not some function that you could expand and find the determinant of, because we don't really. These damn things we're calculating numerically from some finite. It's kind of hard to imagine it, but these analytic. We're taking a finite element simulation with maybe 10,000 unknowns, and then we're producing a solution and analytically extending that.
Mm-hmm.
So there's not sort of like you can't pull out something like the characteristic polynomial. There's no function you could extract out of this. Not that I know of how to do. I've just simply numerically just brute force taking this huge matrix and searching around for when it has eigenvalues of 0.
Yes, thank you.
Can you write it as a generalized eigenvalue problem?
What do you mean by a generalized eigenvalue problem?
So what would it be? AX equals lambda BX?
No, it's way more complicated than that, because it's hard to imagine how complicated this element here is. Yeah, it's buried into this matrix here is just, yeah, it's every element in the matrix is some different analytic function, basically.
Okay.
Yeah, so there's no simple way out to try and find it. So searching the whole complex plane for the zeros is kind of a painful process as well. But remember what these zeros are, these complex zeros, is they aren't as mysterious as they sound. Because what happens is if you took away the fluid, the thing would have real eigenvalues, right? It would have 1 to this mode, 1 for this mode, 1 for this mode, right?
Yeah.
Okay, yeah. So if we put the fluid in here and we have the density to be very small, like a millionth of a zillionth, then in those modes will no longer be real, but they'll have a tiny imaginary part, right? They'll almost, you know, a fluid that's got a density of 1,000,000th and a zillionth is not going to make any difference to this mode, but so it puts the teeniest imaginary part, and as the fluid gets denser, then the imaginary part becomes bigger. So basically those zeros in the complex plane are what's happened to these original modes. They've moved into the complex plane. So that's the origin of them. So basically the eigenvalue that was here in the self-adjoint kind of nice case is persistent. It doesn't disappear. It just becomes complex with the addition of the fluid.
Wow.
Yeah, and they change their form and all that. And that's a standard sort of process that can happen, you know, to lots and lots of problems where you have some damping. The damping is making that frequency complex, isn't it? It's just that the damping is very complex.
And these eigenfrequencies depend on the shape of the structure you're considering.
Oh, very much, yes, very much. Yeah, very, very much. And also, you know, the shape of if you put a thing around the front here, it would change the way, it mightn't change this mode very much, but it would change how it interacted with the fluid and all kinds of things, yeah.
What shapes are you considering? Rectangular or?
Myself, I just coded up a rectangular, very simple stuff, you know, to model ice shells, and I can make them triangles and things. But these guys in Croatia who I work with, they built a finite element model of a container ship. You know, every element here, all the superstructure, with the purpose of accurately modeling the motion of the container ship. And then I took their code, their results that they outputted, and tried to find these zeros in the complex plane by an approximation method, and then produce those results. Because I couldn't go, there's no way their code could run into the complex plane. They didn't have that option, and it wasn't going to be something they wanted to code up.
Well, thank you.
Right, any final questions? Right, well, let's leave it there. Thanks again, Mike. That was no
worries. Thanks a lot. Thanks for the opportunity. And I hope I'll be down to, we're not so far away, so I'll hopefully come down and see you sometime soon once we get out of this, whenever that happens. Yeah. See you all.
Thanks very much. I really enjoyed that talk.
Bye-bye.